Before we go and do another example, let's take another look at another connection here. So we talked about a number being a root, x minus that number being a factor, and the division giving 0 as a remainder, and f of that number being equal to 0. Well, there's another thing. X-intercepts of a polynomial. So the graph of a polynomial of degree n intersects x-axis at most n times. So if you have a cubic, at most 3 times, quadratic, at most 2 times, linear, at most 1 time. So imagine we had this polynomial already factored out. So we can easily see that we have some roots here. So this factor is telling us x equals 1 is a root. This factor is telling me x equals minus 2 is a root. And this factor is telling me x equals 3 is a root. But those are only 3 roots. Now, I must have 6 roots because this has a power of 2, this has a power of 1, and this has a power of 3, meaning if I multiplied this whole thing out, I would start with x to the 6th. Okay, so I must have 6 roots, meaning some of these are repeated. What's nice is in this factored form, I can see how many times it's repeated. So x minus 1 squared tells me that this one is a double root. The x minus 2 is a single root. And the 3 is a triple root. So I have 3 3's, 1 minus 2, and 2 1's, total of 6, including the double counting. And look, if you look at the graph here, we see the x-intercepts of minus 2, 1, and 3. And those are indeed the roots that we found. So in addition to being a root, if you find a real number as a root, then that corresponds to an x-intercept on the graph. So it could be real, or it could be, rational or irrational. It does have to be a real number. So any complex roots would not correspond to a x-intercept. So what we see is that the multiplicity of each root c corresponds to the power of x minus c in f of x. So that's why up here we saw that 2, 1, and 3 corresponded exactly to how many times each one of those roots was repeated, and that gives the multiplicity of that root. So the factored form tells us a lot of information.